welcome back to a new video. Today's topic is insertion sort. Insertion sort also a sorting algorithm that relies on comparison. But to first understand insertion sort, let us consider this example. Imagine we have a pile of unsorted cards like the one I'm having here, and we want to sort these cards in order. How shall we do that? First, we pick a card one by one. So let us pick a card. What we have? 7. So we write 7. Let's pick another card. 6. We compare 6 with 7. 6 is less than 7, so it should be here. Let's pick another card. 10. We compare 10 with 7. 10 is greater than 7, so it should reside here. 3. We compare 10 with 3, it's smaller. With 7, it's also smaller. With 6, it's also smaller. So it should reside here. Now we have 8. So we compare 8 with 10. 8 is smaller than 10. So we should be here. 7 with 8, 8 is greater than 7. So 8 must reside here. We have 2. We keep the same process. And finally 5. We compare 5 with 10, smaller. 5 with 8, 5 with 7, 5 with 6, 5 with 3, it's greater, so it should reside here. So how shall we transform this example, an example composed of deck of cards, to an unsorted array, unsorted efficiently? So here is the code for the insertion sort algorithm. It first takes an array A and integer n representing the length of the array. It initializes a key which will represent the card we are picking at each time. It iterates for I equals to 1 until reaching n. It picks a card at each time representing A of I. It initializes a variable j, and it keeps a while loop while j is greater than or equal to 0 and array of j is greater than key, meaning the A of j here is greater than the picked card. We shall swap and move A of j plus 1 into A of j, decrement j by 1, and finally place the key in its final position and its correct position. Now let's simulate the array A on this algorithm. First, the chosen key is 4, because A of I is now 4. So j is pointing at 5. Here, j is greater than or equal to 0 and A of j is greater than key. So A of j plus 1 will become A of j. We decrement j by 1. J now is no longer equal or greater than 0, so it breaks the while loop and finally places A of j plus 1 to the key. So A of j plus 1 will be equal to the key, which was previously 4. The while loop has finished, so we continue. I is now equal to 2. Here the key is 8. So j now is pointing at 5. We compare. A of j is not greater than the key because 5 is less than 8. So the while loop never executes and A of j plus 1 is still equals to key, which is 8. We continue iterating, reaching I equals to 3, which is 1. J is here. This is the key. So we compare the key with A of j. The key is less than A of j, so 8. Also the key is less than 8, is less than 5, so the key also is less than 4, so 4. Now j is pointing here. The while loop will execute. J is no longer greater than or equal to 0, so this line will execute. A of j plus 1, which is the element right here, will become equals to key, which is 1. Now we continue iterating with I is equal to 4 now, which is 10. So the key now is 10. We compare the key with A of j, which is the element before the key, and found that the key is greater than A of j. So here the while loop will never execute, and we continue with the next iteration. Now I has become 5. Now we reach the final iteration with I equal to 6. The key now is pointing at 3 and the j is pointing at 14. 14 is greater than 3, so we shall put 14. The same goes to 10. The same goes to 8. So when we reach 1, we found that 3 is greater than 1, so the while loop here never executes, and the A for j plus 1 will be equal to p, where j will be pointing to 1. So A for j plus 1 will be equal to p, which is 3. So now we have a sorted array composed of 1, 3, 4, 5, 8, 10, and 14 using insertion sort. Now let us talk about the time complexity of insertion sort. The best time scenario occurs when the array is already sorted, where the while loop is never executing because A of j will be never greater than the key or the big card. So the only iterating loop will be the outer for loop, which will iterate from 1 to n, which will result in a big O of n. The worst case scenario occurs when we have a sorted array in reverse order, where the while loop will have to iterate all over reaching 0 to place an element in its final position. You can imagine that as picking a card and compare it with the rest of the cards you have in the deck. You have to compare it with each card until placing it first. So the worst case scenario will result in a big O of n squared. The average case scenario for insertion sort is closest to the worst case scenario of insertion sort, which also will result in a big O of n squared, where the while loop is sometimes iterating until reaching 0, and sometimes it's iterating until reaching a certain j, and sometimes it's never iterating. However, it's proven that the average case scenario is closest to the worst case scenario. In a nutshell, these are the time complexities for insertion sort. The best case scenario is big O of n, the worst and the average case scenario is big O of n squared. This has been the CS Tutor. Thank you for watching. If you have any question, drop them down below, and see you next time.